is also called an inverse square law. That is because we can say that force, if you ignore the masses in the big G, force is proportional to the inverse of the distance squared. Okay? There is a classification of equations, of physics equations that are known as inverse square laws. And why that is important for each one of these is because of, well, how it works. Take a look at this graph. Okay? Basically, this says that the further away you get from the Earth, what happens to the force of gravity? It approaches zero. It never actually gets there, but it approaches it for a very, very long time. And by the same token, it also, so this goes really, really close to zero really fast. And by the same token, as you get closer, it gets really, really big. Okay? We're kind of in this sweet spot around there. Magnetic field. Okay? All right, you guys play with magnets, right? And sometimes you can feel that magnet thing when they're really close. All right? And then like you move it like an inch away, feel nothing. All right? It's like it's there and then it's not there. That's what this is. That you're feeling the effect of an inverse square law. I mean, it's really, really big, really, really fast, and then it gets really, really zero, really, really fast. Okay, so when we talk about an inverse square law, that is the shape of it. Something is proportional to 1 over something else squared. Now, why would I be referring to Newton's third law in this one? Any ideas? All right, Newton's third law is about two objects. Newton's law of universal gravitation is about two objects. It obeys the same rules. So what that means is the force of 1 on 2 is equal in magnitude and opposite in direction of the force of 2 on 1. That's what that 1, 2, 2, 1 thing. Now, implication of this, just in case you haven't realized this, this is about really big things, right? A lot of times it's really big things. But it's also about the fact that the Earth is pulling on us, right? Whatever our weight is, we are pulled on by the force of gravity. Well, however much the Earth is pulling on us, I would like to remind you that we are pulling on it with the same amount of force. Okay? So the force of the Earth on me is the same thing, is equal in magnitude and opposite in direction of me on the Earth. And yet, I fall towards the Earth. The Earth does not fall towards me. Why? Greater mass, right? Okay, so that's basically it. The magnitude of the mass is why we fall and the Earth doesn't. Okay, that is why we fall and the Earth doesn't. Basically, you guys remember the bug in the bus example? We are the bug. Okay? We are the bug. So, actually, let's keep talking about the magnitude for a second. I want to show you something. Okay. Now, there's a reason why we only feel the effect of the force of gravity when we are talking about something on a planetary or interstellar level. We're going to do a magnitude check right here, okay? All right, we're going to look at the times 10 to the portion of these values, okay? So G is times 10 to the negative 11th. The Earth, all right, so that's really super duper tiny. The Earth is times 10 to the 24th. Okay?
So 1 times 10.
Yeah. Right now I'm only looking at the 10 to the portion. Now, as we are standing on the surface of the Earth, that is basically 10 to the 6th meters. Okay? And the r is squared. Do all those numbers make sense? You understand why I'm putting them there? Okay. Exponent rules. When you are multiplying exponents, what do you do to them? All right. So that means we've got, in the top we're going to subtract them because it's negative 11 plus 24. That's positive 13. What do you do when you square an exponent?
You add it.
Multiply. You're going to multiply. You add or subtract when you multiply or divide. You multiply when you're squaring something. Okay? So that gives us 10 to the 12th. I reduce that down. That is 10 to the 1 or 10. So for us, so basically on Earth, right? That's approximate of our force of gravity. Okay? That is the force of gravity. And the reason why the Earth has to be so big is because that times 10 to the negative 11 is so flippin' tiny. Okay? Now the cool thing about this is they figured out that number, so for a very long time they didn't have this equation. They knew that the force of gravity is proportional to m1, m2 over r squared, but they could not figure out the constant. So they figured out the constant with a pretty crazy experiment in terms of how precise it had to be. It's called the Cavendish experiment. We'll probably talk about it a bit later, but I want you to realize that I think that was in the 1600s. I want to say you're still talking the plum pudding model of the atom. All right? So they were getting things down to times 10 to the negative 11th when there was no clue of a nucleus. All right? Think about like the size issue, the ability to conceive of a size times 10 to the negative 11th as a thing and not just a bunch of zeros on a piece of paper. That they were able to get to that's pretty freaky. But now, let's see this. Well, we can talk about it this way too. I do this as well. Let's also talk about, this happens for every object in the universe. Every object in the universe. So right now there is a force of gravity acting between each of you guys. So let's figure out why we don't feel that, why we're not always running into each other. Okay? So we're going to do the same idea. So it's 10 to the negative 11th is the value of g. So that was like the planet. This is just two people on the planet. Okay? So being exceptionally generous in terms of size, we'll say that a person is like 10 to the 3rd kilograms. That makes it, is that hundreds? No, that's really bad. 10 to the 2nd kilograms. Okay? So you have two people are both 10 to the 2nd kilograms. It doesn't really matter what the actual number is. We're saying 10 to the 2nd. And they are approximately 1 meter apart. So let's figure out what that happens. So it's 10 to the negative 11th times 2 is, well, negative 11 plus 2 is negative 9, plus 2 again, negative 7. So it's 10 to the negative 7 over 1. So that means that the force of gravity that we feel is on magnitude of 10 to the negative 7. How's it go? Tenths, hundredths, thousandths, 10,000s, 10,000s, 100,000s, millions? Okay, so there is a force of gravity between you and every object, you and every other person, but it's on the scale of a millionth of a Newton, which is why we don't go running around bumping into each other. All right.
Is 10 to the negative 11 power supposed to be g?
Yes, that's the one that comes from, that's from the constant of g. Thank you for
So
clarifying.
it doesn't really matter if it's like on the numerator, it could be on the side or...
Yeah, because no matter what happens, that's kind of on top. You have to have the line. Yeah, we can put it on the side or on top, it doesn't really matter. So that's why only things that are on a planetary scale have a force of gravity that can be felt. They have to be really, really big. All right, so now let's talk about the direction. Now, we know how. We just said that there's a force of gravity acting on everybody. reality is, all right, so I'll actually get to that in a second. So what is the direction of the force? Now, there will be times when you are asked, what is the difference between the force of gravity and the force of something else? And you're supposed to like compare and contrast. Here is one way that you can always put down that they are different. Almost. I gotta get the red. Okay? And that is that the force of gravity is an attractive force. It always pulls in. It pulls towards the center of each object. So if anybody in this room happens to have self-esteem issues, please know that you're attractive. All right? Everybody is attractive. Okay? Because all forces of gravity are attractive, even if they're only 1/1,000,000th of a Newton. Okay. All right, now we're not going to make that creepy, any creepier than it has to be. But I just want you to understand that that's what's happening. Okay? Now, again, because of its Newton's law, Newton's third law, it is also considered, a lot of times you will see the negative sign in front of there. Okay? What that negative also tends to mean is that coming back, right? So if one's being pulled this way, the other one's coming back. Pull out your pink sheets, please. This has the absolute value sign on it. What that's telling you is that basically that absolute value is taking care of the negative if it's in there. Okay, so just keep that in mind. Okay, so, well, we're going to get to that one today too. All right. So that is kind of our key points in universal gravitation. Done. Got to solve. Now let's go ahead and we are going to discuss proportional reasoning using universal gravitation.